So the outline for this session is I'll first talk about what is linear programming, and then talk about what are objective functions, what are constraint, and how we can use these concepts to be able to solve some of the very interesting real world problems. And then we'll talk about real world problems. We'll take an industry problem and we'll solve with R. We'll formulate the problem and we'll solve it using R, and then we'll talk about what R package is to be used, and finally we'll solve the linear programming problem using R. So what is linear programming? Well, linear programming is a mathematical technique, so that's one thing to note. This is one mathematical technique for maximizing or minimizing a linear function. Okay, and we'll see what a linear function is of several variables, okay, such as output or cost. We'll understand this definition in detail, so we'll just talk about few things that I have highlighted here. One is maximizing, the other one is minimizing. So when we talk about maximizing and minimizing, we are essentially optimizing, right? Since in a company we want to maximize profit and we want to minimize cost. So one example of it, you might have heard about linear regression. So in these regressions we have minimize the cost function. One of the major use we can relate to, because we have learned so much about linear regression and many other type of regressions. So where are we going to use this in real world? Well, we're going to use this in maximizing profit, minimizing cost, and that happens in many manufacturing companies. How much to produce, given certain constraints, and then it's also used in production planning. Pricing of products is used a lot. It's used in supply chain management. So every linear programming problem will have two things: the function to be optimized or to be either minimized or maximized, and the set of constraints. So here is an example. We have this function. So g is a linear function of several variables, x1, c2, x2, up to n number of things. Okay, so x1 and x2 are known as the decisions variables, which we want to find out. Okay, z is yet not known to us. We want to maximize z or minimize j. Okay, and c1, c2 are the constants already given to us. We know this a priori. Then we have constraints that we want to maximize g with respect to certain number of constraints, and these constraints are also in equation form. Either it is going to be equal to something or less than something, less than equal to something. That would be the case. So this is a constraint that the linear combination, a linear product of the a11 x1, a1 to x2 should be less than or equal to b1. So this is one constraint. So given this constraint, we have to maximize this. Given this second constraint, we have to maximize it. Okay, so just trying to understand what these variables are in the previous slide. Objective function, what we have seen is nothing but g that we have seen is a combination of decisions variable x. Okay, so x are decisions variable. So you just have to remember this, because these variables are to be found out from optimizations, and they are always associated with some of the cost efficient CJ, we're calling it CJ. So, and CJ, the constant values are given to us. Okay, and then we have set of m constraints which are taken into consideration while minimizing or maximizing. Okay, and we might have boundary conditions for the decisions variable, like many cases where decisions variable have to be positive. Now, another thing that I like to introduce to you, that LPP problems can be solved by using a number of techniques, mathematical tools, and one of the way that we can use is the simplex method, which is a very popular one. So here is an example. A small business sells two products. So we have got two products, we call that as product 1 and product 2. Each ton of product 1 consumes 30 working hours. Each tons of product 2 consume 20 working hours. Okay, so I've got product 1 and we have got product 2. Product 1 consumes how much hours? 30, and product 2 consumes 20 hours. The business has a maximum of 2,700 hours. So that's the maximum the business, the factory can spend in terms of in order to produce product 1 and product 2. So that's one constraint already given to, right? Constraint is nothing but a limitation or a cap on something or a limitation on something. Okay, so working hours for a period considered. As for machine hours, each ton of product 1 and 2 consumes 5 and 10 machine hours respectively. So there are 850 machines are available to us. So that's another constraint. So we have a constraint on the man hour, which is 2,700, and we have also a constraint on the machine hours, which is 850. Each ton of product 1 yields $20 million of profit, while product 2 yields $60 million of profit for each ton. So for each ton we have the profit in place, so I guess the problem is already now clear. So we are trying to, maximize profit here, right? That's the problem we have with us. For technical reasons, the firm must produce minimum 95 tons. So that's another constraint. So the minimum number of product 1 plus product 2 should ideally be 95 or more. So that's one requirement from the business side. So this is a target to be met at any cost. So that's another constraint. We need to know how many tons of product 1 and product 2 must be produced to maximize total profit. So here is what is our main agenda. So we need to maximize total profit, and the question that has been asked to us is how many number of product 1 and product 2 are to be produced to maximize profits, given the constraint that we have talked about, given the information that we have been given. Okay, so we have the constraint with us and we have a clear objective given to us that we need to maximize profit. So just tell us how many products to be manufactured, and how many of them are going to be product 1 and how many of them are going to be product 2. So the decision variable for us is the number of product 1 and number of product. X1 is the number of tons produced or sold by product 1. So that's one thing we will assume. X2 is the number of tons to be produced. Okay, so we want X1 tons to be for product 1 and X2 tons to be for product 2. The cost coefficient of these products, of these variables are 20 and 60. We have been given the profit that is made from product 1 is $20 million and it's $60 million from product 2. So the cost coefficients are 20 and 60. Remember C1 and C2 we talked about in the definition. That's exactly what it is. Therefore, the objective function is defined multiplying each of these variables and its corresponding coefficient. So objective function, if we is defined as G, is equal to 20x1 plus 60x2. We have several constraints. We have working hours constraint, and the total number of working hours used for product 1 and product 2 is equal to 30x plus 20x, 30x1 plus 20x2. Has to be less than 2,700 hours. Okay, so how do we come up with 30 and 20? Well, 30 hours is taken for one product, right? And 20 hours is taken for product 2. Similarly, for the man hours, we'll just use the same equation, same way of formulating. Well, we have 5 hours taken for product 1 and 10 hours taken for product 2, and that summation, product sum product, should be less than 850 because that's the maximum available to us. Total units to be produced should be should be greater than or equal to 95. So x1 plus x2, the sum of x1 and x2 should be greater than 95. So that's the third constraint. So we have this problem in place. We have to maximize profit, and the profit function is 20x plus 60x2. x1 and x2 are the decision variables. Decisions variables are the variables to be found out from optimization. So we want to know what exactly is the value of x1 and x2. We want to know the actual values, right? And we have constraint. Now, in order to solve this in R, we'll be needing a package called LP solve. All right, so we'll do this now. okay, I'm going to show you the screenshot of the the R code, and you can use this code to do it on your own. And I highly recommend that in order to be able to understand it well, you do it by yourself. Use this code that is given on the screen, and you will be able to understand it better. So we'll first load this package after installing it, and then we'll define some of the parameters that we have with us. So here is the objective function. So objective function has 20x1 plus 60x2. So we create a matrix with 20 and 60, and we call that as object under dot fun. So that objective function, okay, that's short form of objective function, and you can give any name. Okay, just have a matrix as such, and then you have you do the same thing for constraint as well. Okay, so we have a matrix for constraint as well. Okay, so we have got three constraints, right? The first constraint has the coefficient value 30 and 20, and the second one has 5 and 10, and the third one is 1 and 1. So we'll put that in the in a matrix form, okay, in the column and row form. And you might wonder, how is that going to recognize the first equation, the second equation, third equations? Given that we have only two decisions variable x1 and x2, and we have defined that here itself, because the number of decisions variable will always be equal to the number of the number of coefficients. Okay, so now it knows that there are two decisions variables. Okay, so if you have two decisions variable, it's always going to take two, the next two, and the next two as the equations. Okay, so it is very clear. Okay, it is understandable, it's very logical, it's something that you do not have to tell R. It always gets it by itself. Okay, and we have constraints, and constraint signature would be important. Okay, constraint direction rather. So it would either be less than equal to or greater than equal to. Okay, and how many of them are less than equal to? So this is less than equal to, and all three are less than equal to, right? All three are less than equal to. I think all right. So I think this should be less than equal to. This seems to be a mistake. Anyway, so just check it out. And I might have made a mistake here, but yeah. So that's the idea. So I'm sure the idea is clear. Okay. Now in the third one, you just put the right hand side value. Okay, the constraint values here. Right here it is 2700. It's 950. And we have got 95, so that you put in another matrix. So the right hand side of the equations, you just put it one place. Okay, now we have the three parameters in place. We have objective function, we have constraint, and we have the values in the right side of the constraint, and we have the direction of the constraint. Now using these four variables that we have defined, we can pass on these variables to the package LP, the function LP, and it is going to solve for us. Okay, so this is a maximization problem. So we need, the first argument is double quote max, so that shows it's a maximization problem. Then we give the objective function, then we give the constraint, then we give the direction of the constraint, and then we give what is there in the right hand side of the constraint. That means the boundary values, right? We call that as a boundary values. We give that, and when all these parameters are given are used as part of the optimization, we'll get the values of x1 and x2. That's the objective for us. That's the main intention of doing these optimizations. Now the information that was given already to this function is defined prior to this. Now you cannot solve this without defining the parameters. So you first have to define these parameters with the given information. So the best way to do is to first use your notebook and define a problem. So you cannot directly go and write a code. I mean, you can always do that, but it's always easy to it's much easier to write it on your notebook and then write your code. That's easy. Otherwise you might make a mistake like I have made one. All right. Now when you run this code, um, you get your solution right away. So we have run this code, and the solution to these problems are x1 and x2, right? And x1 is 20 and x2 is 75. Okay. Now if you go back to the problem and test it out, you will see that all constraints are met, all constraints are satisfied. You won't find any constraint to be violated. Okay. Now one of the constraints we can check is that the total number of products produced for product 1 and product 2 should be greater than equal to 95. When you add them, 75 plus 20 is exactly 95. So that constraint is satisfied. Right? Similarly, if you can check other two constraints, it is also satisfied. Another constraint that is satisfied is the both are positive, so that's quite clear to us. All right, so solution is very clear to us. Now we can tell the industry or the factory that look, given the constraint, if you want to if you want to maximize your profit, you need to produce 75 tons of product 1, 75 tons for product 1, and 20 tons for product 2. Okay, so these are the solutions. This is the solution for this problem. Now the same can be extended for many other reasons, right? You could take advertisement spending, right? You have a problem where whether you should spend, how much money you should spend for advertisement on Facebook or Twitter. Okay, if you're working for advertisement firm, you can use this as one of the problem. Many times you would be coming across cases that where a bank would ask you to find out what should be the optimal interest rate that you should charge for let's say 3 different products that the bank is selling. Okay, so that could be one of the problems. So there are several industrial problems that can well be solved using this, and simple to use. There's a few lines of code, but you can solve very complicated problems, very sophisticated problems using just few lines of code. Alright, so we have come to the last part of the session where we'll just talk about the real world problems. Okay, as I've already said, the LPP is heavily used in many problems worldwide, in manufacturing, in aviation, in supply chain, in shipping industry, in military, in government actions. I mean, you cannot name an industry which doesn't use optimizations, and it's heavily used everywhere, and it's has been there for over many years. And probably it was started during the Second World War. It got popularity during the Second World War when mathematicians formulated optimization problems for a war strategy and so on. So yeah. So that's a different thing. I can always read out more about optimization or operation research LPP on Wikipedia as a good resource to learn the history of LPP and its uses. So it can well be used in supply chain to know what would be the optimal route. In supply chain, the important part is how to reduce the supply cost, how to ensure that the efficient supply of goods and services will be done with less cost. Okay, so that is one area where you use LPP. Pricing analytics, where you have multiple products and you need to know what should be the good price of these products or the quantity of the products, so that you optimize the profit. In financial analytics, you talk about interest rate, fixing interest rates, and then combining different products and so on. So this is where you use LPP, linear programming, quite a lot. Marketing is where it has been used for a very long time. Marketing spend, where you have a budget which is a constrained budget. You have to use your budget in many different marketing areas, and the decision to spend money on different areas of marketing is something that is done by linear programming. Advertisement is also a new area, especially social media advertisement is where you have many options. You have Twitter, you have Facebook, you have YouTube, you have Google, many options to choose from. And in order to optimize your advertisement spend and the profit out of it, you can formulate a linear programming problem and solve it and find out an optimal solutions. Thank you so much, and please subscribe to us.